Hi everyone. So as always, we start with the learning objectives that we will check at the very end of the class, but feel free to go through them if you want. Today, again, we're going to do lots of things, but because this is SL, this is really concept heavy, but the problems themselves won't be so hard. When we go to HL, things will change, and then it will be the opposite. There will be very little here, but the problems will be really complicated. The first idea that we're going to discuss is that of a wavefront, and again we did that in the IGCSE. So imagine that there's a source of light, for example, that is transmitting some waves. So each wave of light is going to be doing something like this, yep, and going in different directions. But if I take a look at the crests, what I can do is I can draw this imaginary line that links all the crests together. Okay, so let's do this in a flat way. So here's one wave, and then here's another one. And imagine that these guys are just traveling next to each other. Excuse me. Then these things here are the wavefronts. This is just an imaginary place where all the different crests are aligned. And if I do this in 2D, where there's a source that radiates in all directions, these wavefronts are circular. So wavefront, wavefront, wavefront. Now wavefronts are very, very useful when we are analyzing how waves propagate, and we will use wavefronts all the time when we're doing optics. One thing that's worth noting about wavefronts is that if we know the speed of the wave, then we know that basically the wavefronts are moving away from the wave at the speed of the wave. So for example, all these wavefronts are moving outwards at the speed of light. And that's why these are circular, because all the points are moving away from the central point at the same speed. Now wavefronts can be like these circles, but they could also be spheres, right? So if this was in 3D, I have a point of light, and then all the little crests are going to be moving away from the light at the same speed, making a sphere in 3D. Or I could have a flat wavefront. So for example, if I have water, I have water like this, and I just push all of this at once, then what's going to happen is that I'm going to create waves in the water doing this, just like the ones I have over here, and then the wavefronts are going to be flat. Now another idea that's very, very useful is that of ray. And the idea of a ray is that it shows us where the wave is going. And to determine a ray, all we need to do is know the wavefront. So if these are the wavefronts, where's the wave moving? Well, obviously, this way, and this way, and this way, and this way. So we can just draw that with a little arrow. And these little arrows are the waves. And notice that the rays are perpendicular to the wavefront. So this and this are perfectly perpendicular, and so is this and this, and so is this and this. This is a general rule. So for example, in this case here, the rays are going to be moving with the wave this way, and therefore we will have, again, perpendicularity between the wavefront and the wave and the ray. So the idea is that rays show us where the wave is moving, whereas wavefronts show us all the points that are at the same phase. And remember, the same phase is the same angle, so that they have the same displacement. So a wavefront will show us all these points have the same displacement. Click, click, click. And a ray will show us, well, and the wave is moving this way, or this way, or this way. Now it's time to talk about something called intensity. And the intensity of a wave basically tells us how much power this wave is delivering per unit of area. So remember, hopefully you remember that power is energy per second, right? So of course a wave is something that's transmitting energy, so a wave is carrying some energy. Then of course, if I'm sitting here, I will not get all the energy that this guy is releasing, because most of it is going elsewhere. So how much energy I will get will depend on how much area I'm spanning when this hits me. Right? So the more area, the more energy that I will get from here. So if I was to envelop the whole source, I will get all the energy that this is releasing. Otherwise, I will get less and less energy depending on the area that I'm at. So the idea is that then, instead of using the notion of power, that would only tell us how much energy this is releasing, what we really need is a notion of how much energy per unit area is reaching me. So, of course, if I'm very far from the source, then most of the energy is going to be lost because it is going to go in all directions. So the energy per unit area that's going to hit me is going to be very little. If I'm very close to the source, then the energy per unit area is going to be much, much more. So we define intensity as the power radiated by the source, which is the energy per second, divided by the area. So this tells us the power per unit of area at a certain point. Now, this really depends. So if I have a flat wave, this is always going to be the same. But in the case of a point in 3D space, so here's a point of light, right? For example, a light bulb in your house, and then that's transmitting light in every possible direction, so that all this power is getting spread out over the surface of a sphere. Now, hopefully you know what the surface of a sphere is. If you don't, here's the formula. The area of a sphere, not the volume, but the area of a sphere, is 4 pi r squared. Therefore, if I want to calculate the power at a certain distance of my little light bulb, then all I need to do is to replace that area by 4 pi r squared. So it's going to be the power of the light bulb divided by 4 pi r squared. And this will tell me how much power is reaching me at that distance. And what's really important about this result is that it goes down with r squared, where r is the distance to the source. So basically what we just found out is that if my source is transmitting in all directions, then the intensity that I'm going to get is going to be, proportional to r minus 2. So when I double the distance, the power gets divided by 4. When I quadruple the distance, then the power gets divided by 16, and so on. Another important property of the intensity of a wave is that it's proportional to the amplitude of the wave squared. And I'm not going to prove this to you because it's complicated, but the idea is that, remember that for example, in simple harmonic motion, the maximum energy is 1/2 of k times the amplitude square. And we know that the power is proportional to the energy, and therefore it has to be proportional not to the amplitude, but to the amplitude squared. Since the power is proportional to the amplitude squared and the intensity is proportional to the power, it follows that the intensity has to be proportional to the amplitude of the wave squared. So what does that mean? So for example, in a sound wave we have sound vibrating, and the bigger the vibrations, the more intensity of the sounds, then the louder the sound is going to be. And it turns out that the intensity of the sound really depends on how wild the vibrations are squared. So if I have vibrations that are, again, twice as wide, then my intensity will be 4 times as wide, and so on. So these are the two things that we need to remember: that the intensity goes down with r squared, and that the intensity goes up with the amplitude squared. The next thing that I would like to talk about is something called the principle of superposition. And the basic idea of the principle of superposition is what happens when I have a pulse traveling this way and a pulse traveling this way and they meet. How is the pulse when they meet going to look like? And what the principle of superposition says is that all you need to do is add up both pulses. So if we know the displacement for this point and we know the displacement for these points, when they meet, all we need to do is add up the displacements for both. So in this case, let's just do this here. When they finally meet, we would have something like, so here's my blue pulse, and then on top there would be the red pulse. So therefore, the shape of the wave is going to be something like this. And this very simple principle is the cause of phenomena like interference that we will study next week. So let's do another example where, for example, now this goes down. Well, if this goes down, imagine that now we have this thing here. Well, again, when they meet, I would have, here's the blue one, but then this one is negative, so I would have to subtract this from the blue one. So I'm going to draw this thing here, and then therefore the wave shape would be something like this. So all we need to do, again, when two waves meet each other, is we just add up the displacements of each point, and then we know the total displacement of the two things when they meet. Of course, these things are moving, so this is going to be changing, right? So at the beginning, so let me just show you in this case here. So in this case here, first, this guy will be here, and then this guy will be right here. So then the wave shape will be this, then goes up, then goes down here, then does this. And then as this guy moves forward, and forward, then we will get this shape here. So the idea is that at each instant we will have a different superposition. So it really makes no sense to say what's the superposition in general. It's like what's going to be the superposition at a certain point. So this guy's moving towards here, this guy's moving toward here. So what happens when they're about to meet? What happens when they're here? What happens when they completely overlap, and so on? And the idea is that what happens is that these two things just get added up, and if one is negative, then it gets subtracted. Next thing I want to consider reflection, which is when a wave hits a certain obstacle and then gets bounced back. And there's two different cases. One is when things are tight, so when the ends are fixed, so for example to a wall, and the other case is when the ends are loose. And the answer to both questions is a different one. So imagine that I have this wave that's traveling this way, so it's going this way, poof, and then it hits a wall. And then we want to know, how will the wave that's traveling back look? Will it look exactly the same? What will happen to it? Well, the idea is that each one of these things is really pushing the next thing up, right? So this thing just like has a certain displacement, and then it's forcing the next thing to go up, and then that's why this goes up. Then this will go down, and then this displacement is being propagated because the points that are displaced here are pulling the next point up. So therefore, when this thing gets to the wall, it's going to try to pull the wall up. Now, I don't know if you guys remember Newton's third law. You should remember it. But Newton's third law says that for each action there is an equal and opposite reaction. So if this guy tries to pull the wall up, how's the wall going to react? Pause the video and tell me. Okay. Hopefully, you thought, well, if this is pushing the wall up, then the wall's going to react by pushing this thing down. And then if it pushes this thing down, what will happen is that instead of having a pulse like this, I will have a pulse that's inverted. And that's what happens when the rope is fixed. So when the ends are fixed and there's reflection, what happens is that the pulse gets inverted. Now, what happens when the extremes are not fixed? So imagine that instead of a wall, the thing just goes back on itself. So have something like this, and then whoops, and I just have a little point here to fix it. Now, in this case, so this goes this way. In this case, there's no reaction force. In this case, this will push this up, 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 and then the same exact thing is going to happen, and the wall is just, and the wave is just going to bounce back exactly the same. So when the ends are not fixed by something like this, then reflection is just normal. There's no inversion. But when the ends are fixed, like for example tied to a wall, because of Newton's third law, I will get an inversion of the pulse. Okay, now we're going to do the hardest thing that we're going to learn today, and it's called polarization. And actually, I told you about this the other day in class for a very brief time. I don't really remember how it came to be, but remember that I had these classes from China, and we were playing with them a little bit. The idea of polarization is that I have a certain wave that's transverse, but it can be transverse in many ways. So imagine that the wave is going this way. This could be either vibrating like this, or it could be vibrating like this, right? So I have several options. In fact, this could also be vibrating like this, or like this, or like this. And in fact, what happens is that, for example, light waves are vibrating in every possible direction. So when I get light from a light bulb, so here's my light bulb. Okay, that's the worst light bulb ever. The waves that come from the light bulb are actually vibrating in every single possible random direction. So like this, like this, like this, like this. So these kind of waves are called unpolarized, because they're just vibrating however they want. Now what I can do is I can use something called a polarizer, and a polarizer is basically a filter that only lets one type of vibration get through. So instead of having them all, it's like, you can imagine it as this little slit, like microscopic slit, that only lets waves that are traveling in this direction get through, and everything gets reflected back or just absorbed, so that waves after the polarizer are only like this. Or I could also have a polarizer that does this, right? And then the waves that travel after it would only be like this. But the idea is that the polarizer only lets waves that are traveling in one certain direction get through, and everything else gets lost. Now, of course, when this happens, I'm basically wasting half of my light. So for example, something that was vibrating perpendicular to this just doesn't pass, but something that was vibrating a little bit like this, a component of it will pass, and then the other one will get absorbed. And the effect of having a polarizer is that 50% of the light is lost. Now, once light is polarized, I can run it through another polarizer. So imagine that I run it through another polarizer that's at a certain angle to it. So this would be my light, and there's a certain angle between the polarizer and my light. And what I would like to know is, what is the intensity of the light that gets through the polarizer? And this is something that a guy called Malus considered for a while and arrived to a certain conclusion. And this one I'm going to prove it to you. Now the idea is that this light, let's just make a little diagram. So here's my polarizer, and here's my light. That's at a certain angle. Now, just because of vectors, only this component of the light is going to survive, and the other component of the light is going to be lost. But this is not the intensity, this is the amplitude, right? This is the electric field, so this is the amplitude. So what's going to happen is that the amplitude is going to get cut, and only this part is going to survive. So using some trigonometry, I would like you to try to calculate this component. So give yourself a couple of minutes, pause the video and do it. Right, hopefully you did it. I don't know if you did, but I'm going to assume you did. So the new amplitude, let's just call it A prime, is going to be the old amplitude times the cosine of theta. Because remember, this is the adjacent side. So then the new amplitude is going to be less than the previous one by this factor, cosine of theta. And now we need to remember that the intensity is proportional to the amplitude squared. So therefore the new intensity, let's call it I prime, will be the initial intensity, so times what? The cosine or something else. Pause the video and figure out what we need to put in here. Okay, hopefully you did this and you saw that since this is squared, this will be a squared times cosine squared of theta. So here we need to put the cosine squared, so that the new intensity will be proportional not to the cosine of theta, but to the cosine squared of theta. And this is known as Malus's law. Malus's law. And it tells us how the intensity changes when light that's already polarized goes through a second polarized. And this makes sense because, for example, imagine that my polarizer was at a right angle to my light. So here's my light, and I have a polarizer that's like this. So the angle is 90. Then nothing's going to get through. And what's the cosine of 90? Well, that's 0. Great. Now, what if the angle was 0? So what if my polarizer were like this? Well, then everything's going to get through. What's the cosine of 0? Then that's 1. So the intensity will be the same. So this law effectively reproduces what we see. And this makes perfect sense because, again, what gets cut is the amplitude, not the intensity. Now, apart from using polarizers, there's another way of polarizing light, and you'd be surprised to know that it's just by reflecting it on a surface. So imagine that I have some water, and I have some light that's coming in, and this light, as you know from the IGCSE, will get refracted. So some of this light is going to go this way, and some of it is going to get reflected at the same angle, which again we know from the IGCSE. Now light, remember, is a transverse wave, so this one, let's just imagine that it's not polarized. So we have light in all directions. It turns out that the light that gets reflected is not like this one where light is going in all directions. It's still going in all directions, but there's one direction that's privileged, and that direction is parallel to the surface. So it turns out that the light that's coming out this way is something called partially polarized. And what do we mean by partially polarized? Well, it's hard to draw in here, but let me just show you. The idea is that if light is coming at us from the screen, so we could have, for example, this part would be very small, and this part would be very big. So even though it's not totally polarized, there is a component that has more field than the other one. And we call that partially polarized. So the light that reflects on a surface comes at us partially polarized. And this component here is the component that's parallel to the surface. So in this case, it would be going on, like in and out of the screen. In fact, there's an angle, and we will do this in HL probably, where this polarization is complete, and then the light that's reflected from the surface is totally polarized. Now, this is important for photographers, because when you want to take a picture of a lake, you don't want to see the glare, right? So what you do is you add a polarizer to your lens. So you have, here's your camera. Okay, yeah, that's a camera. And then you add a polarizing filter here, and this allows you to get rid of the polarized light that's coming from the reflection on the surface, which means that then you're able to see what's under the surface without having to worry about glare. And that's pretty cool. Okay, we're done again. Again, it was a lot of stuff, but you're not required to know it in a lot of depth. You will be required to know things in a lot more depth when we go into HL, but by that time, we will know a lot more about circular motion, and then the equations will make a lot more sense. So let's see if we understood what we're supposed to understand. First thing, define wavefronts and rays. Remember that we have a source of light. The wavefronts are places where the troughs are all the same, and then the rays are perpendicular to the wavefronts. Define amplitude and intensity. Remember that the amplitude is how much things deviate from the middle, and intensity is the power per unit of area. Sketch and interpret diagrams involving wavefronts and rays. Well, there's really nothing to learn here. Solve problems involving amplitude, intensity, and the inverse squares law. Well, good luck with that. Sketch and interpret the superposition of pulses and waves. We did that. Describe methods of polarization, either a polarizer or reflection from a surface. Sketch and interpret diagrams illustrating polarized, reflected, and transmitted beams. We just did that. And solve problems involving Malus's law. Well, I taught you Malus's law. Now we just need to solve the problems. Alright guys, so thank you very much for listening, and I'll see you in class.